Hey super scientists, we're looking at page 5, your periodic table, and we're going to be color coding that together. We're looking at group 1 first, the alkali metals. Alkali metals are the most reactive metals on the periodic table. They're rarely found alone in nature, so they're usually found combined with other elements in a compound. And their unique chemical property is that they catch on fire and explode when they're mixed with water. So the alkali metals we're going to color code in pink. We're color coding the box around this information in pink as well to kind of use as our key. And then we're going to color in lithium down through francium in pink too. So you'll notice that hydrogen, I have not colored that in. Hydrogen is not an alkali metal. So although it is at the top of group 1, it is not a metal. It's all by its lonesome. So we're leaving that one white. And I also circled this number here, this 1. So at the very top of each of these groups on your periodic table, that number indicates the group number. So you can use that as reference for the other groups. Group number 2 is the alkaline earth metals. So the alkaline earth metals are the second most reactive metals. They're reactive in a little bit of a different way though. In terms of flammability, or when they catch on fire, they're going to be used in fireworks. So they produce different spectra, different colors. So the alkaline earth metals, we're going to color code in purple, and we're coloring beryllium down through radium in purple as well. So each of these different elements, when they are used in fireworks, are going to produce a different color. So barium's kind of a yellowish green, magnesium's going to be white, strontium's kind of a purplish red color. So they're each used to produce a little bit of a different color variation. Our next section is pretty large. This is our transition metals. So the transition metals are going to cover group 3 through 12. They are going to be able to be found alone and also in compounds naturally. So they can be found in both ways. They have a high melting point and a low specific heat. And that's really important for some of the everyday uses that we use transition metals for. So because they have a high melting point, they will not melt until they get super high temperatures, which makes transition metals good for using for things like pots and pans. So just imagine if you were going to bake some cookies and you got these nice chocolate chip cookies you're going to put it in the oven and enjoy later, and you put them on a pan. Well, that pan has to go in the oven and gets like 350 degrees or so for an extended amount of time. You don't want that pan to melt. You want to be able to enjoy your nice chocolate chip cookies later. So it'd be pretty bad if you got that pan out of the oven and there was metal all melted and stuck to your chocolate chip cookies. That would be very appetizing. So because metals, the transition metals have a high melting point, that means they're going to be used for common household purposes. They are not going to melt until they encounter extremely high temperatures. They also have a low specific heat, which again is good for pots and pans because that means they're going to heat up pretty quickly. So since they have a low specific heat, they are able to change temperature pretty quickly. So we're coloring green for the transition metals around your key here, and we're coloring scantium down through actinium and all the way over to zinc and niobium at 112. Our next couple groups of elements are going to be just the family names, and the reason why that is set up that way here on your color coding is because these elements are in mixed groups. So the boron family is group 13, carbon family is group 14, nitrogen family is group 15, oxygen family is group 16. And those mixed group elements are going to have nonmetals at the top, metalloids kind of in the diagonal on your zigzag, this little staircase, and then your metals at the bottom. So we're going to look at those different groups separately in a little more detail to kind of analyze their properties. So the names of these different elements that are listed at the top as the family name, that's named after the element that is at the top of the family. So boron is at the top of this group, so it's called the boron family. Carbon's at the top of this group, so it's called the carbon family, and so on. So we're going to color the boron family yellow, boron down through thallium. We're coloring the carbon family brown, carbon down through lead. The nitrogen family is orange, and that is nitrogen down through bismuth. And oxygen family is blue, kind of a dark blue color, oxygen down through polonium. Our next group, group 17, these are your halogens. These are the most reactive non-metals. We said the most reactive metals are on the left-hand side of the periodic table over here. Our most reactive non-metals are going to be group 17. And these are the halogens. So if you use your stems to break down this word, halo means salt, gen means origin or producing. So literally, these are salt-producing elements. So these elements during chemical reactions are going to form salts. It may not be an edible salt, but it's some type of salt residue. So we're coloring these most reactive nonmetals red. So go ahead and color code your key here as red, and that's going to be fluorine down through acetine. Group 18 elements are the noble gases. The noble gases are going to be elements that are unreactive. So they do not like to combine with other elements during chemical reactions. These are also referred to as inert. So if you see that word inert, inert, that's just referring to how the noble gases are unreactive. They have a full valence shell of electrons. So remember, the valence electrons are on the outermost orbital shell, and they don't like to form compounds. The reason why is because they have a full valence shell of electrons. So they follow that octet rule to where they have eight valence electrons in their outermost orbital shell, so that helps them to be happy little elements where they don't want to give any electrons away and they don't want to take any electrons. They just really want to be left alone. They are the stuck-up elements of the periodic table. So that's group 18. Noble gases, helium down through radon. We're coloring in black, so we can just outline in black and color those elements as well. Down at the bottom here, we have the lanthanides and actinides. So the lanthanides, we're going to color in light green or kind of a lime green color. We're outlining the key down here in light green as well. The top row is going to be the lanthanides. Now that name comes from this element here, 57 lanthanum. You may have noticed that there's a jump in the atomic numbers from lanthanum to hafnium. It goes 57 to 72. And the reason why you have that jump there is because that accounts for the lanthanides and actinides down here. So we have 57, and then down here cerium, it starts 58, all the way over to 71, lutetium. So that whole section really gets inserted by the atomic number right here where I have the arrow. So these guys have their own unique properties unto these groups. So the lanthanides have similar properties, the actinides have similar properties, and so they are removed from the rest of the periodic table, but they are metals. So the top row, the lanthanides, they're silver metals. They have sort of a soft texture, and when they are exposed to oxygen, they rust, or the other term is oxidize. So your stem oxy refers to oxygen, presence of oxygen. So that's one unique characteristic of the lanthanides. The actinides are the bottom row. So the actinides are going to be from thorium right here, TH, all the way over to LR, lawrencium. And again, these elements get inserted right here from 89 to 104 in this little gap right here. And they are named for actinium, AC, so the actinides get that name from actinium. So the actinides, they're all going to be radioactive, and so they're pretty unstable. Some of them are going to be magnetic or weakly magnetic, and most of these elements can be in a crystalline state, so their molecules are in sort of a specific pattern. Most of them are going to be synthetic as well. Your term synthetic means man-made. Syn is together, the means put, so literally they're put together, they're manufactured. So these actinides on the bottom row here, you'll notice that the atomic mass is in parentheses, and that is because a lot of them are so unstable that they only exist for a few seconds. So since a lot of them are synthetic, they're going to be created in particle accelerators where scientists will smash a couple of atoms, a couple of nuclei of different atoms together, and when that occurs, a lot of them are going to be unstable, so they break down, they decay in a matter of a few seconds. So scientists don't have a whole lot of information about some of these elements because of that. So that is why you have this number in parentheses, because there's not a lot of different isotopes or a lot of different measurements of the atomic masses of those different nuclei and those different isotopes. So you should have your periodic table color-coded on page 5.